Chapter 13 takes us into the formulation of confidence intervals for means and proportions. So these will be our first inferential statistical applications. Confidence interval is a synonym and more common term for interval estimate. A confidence interval is the likely range within which a population parameter is located. There are two key confidence intervals. The most important is the 95% confidence interval, the range within which one is 95% confident that a population parameter is located. And sometimes researchers calculate a 99% confidence interval, that being the range within which one is 99% confident that the population parameter is located. Occasionally, a 90% confidence interval is calculated as well. Let's review the central limit theorem as it applies to the sampling distribution of the mean. The CLT states that the mean of the sampling distribution is the population mean, that the standard deviation of the sampling distribution is determined by dividing the population standard deviation by the square root of the sample size. Further, it states as sample size increases, the shape of the sampling distribution approaches normality. And we added in Chapter 12 the notation that when n is greater than 100, the shape of the sampling distribution is pragmatically very close to normal, regardless of the shape of the population from which the infinite number of samples of the same size is drawn. A real-world problem is that in real-world research, we don't know the standard deviation of the sampling distribution. In other words, to determine that, we divide the standard deviation in the population by the square root of the sample size, but we don't know the standard deviation in the population because we're working only with one random sample, not with the full population. That being so, as things stand now, we cannot form confidence intervals. Let's again invoke some pragmatism so that we can indeed form confidence intervals. And pragmatically, when sample size is 100 or greater, the following formula provides a very close estimate of the standard deviation of the sampling distribution. So we're going to be able to use this estimate rather than the actual standard deviation of the sampling distribution. So we can get a very good estimate of the standard deviation in the sampling distribution, provided that n is 100 or greater. To do that, what we need to do is take the standard deviation in our single random sample. We're simply going to be choosing one random sample and divide that by the square root of n. And that gives us the symbol on the left side of this equation, and that is an estimate of the standard deviation of the sampling distribution. And this is a very good estimate when n is 100 or greater. So let's sketch out the theory that underlies formation of a 95% confidence interval. We're going to presume in our discussion that n is greater than 100. Given that n is greater than 100, the shape of the sampling distribution is going to be very close to normal. And further, point 1 of the central limit theorem states that the mean of the sampling distribution is the population mean. Reasoning from these 2 points, we can determine that 95% of the sample means, 95% of the means in our sampling distribution, will be located within 2 standard deviations of the population mean. And so we're going to be using in our formulas this estimate of the standard deviation. So 95% of the sample means in the sampling distribution are within 2 standard deviations of the population mean. So this is just another way of saying that for 95% of the means in the sampling distribution, if we extend a line 2 standard deviations in both directions from that sample mean, well, for 95% of sample means, this line will include the population mean. This is just common sense following from the prior point. If 95% of the means are within 2 standard deviations, then for 95% a line extended 2 standard deviations in both directions will, so to speak, capture the population mean. So 95% of the sample means are within 2 standard deviations. In real-world research, we don't know the population mean. We don't know with certainty whether a particular sample mean is within 2 standard deviations. But it's the case that we do know that 95% of sample means are within 2 standard deviations, so that therefore for any given sample mean we can be 95% confident that a line extended 2 SDs in both directions will indeed include the population mean. Now, one study sample is a random sample, and now let's presume again that n is greater than 100. So the study sample is just simply treated as one random sample in the sampling distribution. In real-world research, it's the only sample, but in relating to our confidence interval theory, we regard it simply as one random sample in the sampling distribution. So we know that for 95% of samples, extending the line 2 standard deviations includes the population mean. In other words, we're 95% certain for each given sample that such a line includes the population mean. And so indeed, if we extend a line 2 standard deviations in both directions from our study sample mean, the study sample being simply one random sample in the sampling distribution, we're 95% confident that that line captures the population mean. In other words, that the population mean is located within the range that that line spans. So, the just described line is indeed a 95% confidence interval. So, what one does to form a 95% confidence interval is extend a line in 2 standard deviations in both directions from the mean of their random sample. And it is the case that 95% of 95% confidence intervals do indeed include the population mean. So in other words, confidence intervals don't always include the population mean, but in the long run, 95% of 95% confidence intervals do so. So that for each given confidence interval that you form in a given study, you can be 95% confident that the population mean is located within the range that that interval defines. Now, on the other hand, in the long run, 5% of 95% confidence intervals do not include the population mean. And that's because 5% of means in a normal distribution are located more than 2 standard deviations away from the population mean. So in any given study, you never know whether the particular confidence interval that you form does indeed include the mean. Though you don't know that, you are 95% confident that this is the case. So this graphic presents some confidence intervals. In other words, perhaps you're drawing some different random samples in our example, and then creating a confidence interval for each. So perhaps, and we're sticking with our child maltreatment example, so looks like for sample A, the mean of that sample was about 8.7. You did various calculations using S divided by the square root of n. In other words, standard deviation in your sample, well, you divide that by the square root of n, and that estimates very closely the standard deviation in the sampling distribution. Then you've got to multiply by 2 to go 2 standard deviations in each direction. So here is the confidence interval that results in your first sample. And you can see that this confidence interval does indeed include the population mean, which is 9. Now, in real-world research, you would not know that it includes the population mean of 9 because you don't have access to the full population data. If you did have access to the full population data, there would be no reason to form a confidence interval. It would be the question of a likely range within which the population mean was located would make no sense. If you had access to the full population, you would simply know it, and you wouldn't go through the process of forming a confidence interval. The second confidence interval, which I've labeled B, perhaps the mean of your second random sample was about 9.5, and so do the necessary calculations. You go 2 standard deviations in both directions, and this interval is indeed one that includes the population mean. And in the long run, 95% of 95% CIs do include the population mean. Here's the confidence interval from random sample C, and just as did A and B, this one includes the population mean of 9. But as you know, 5% of 95% confidence intervals do not include population mean. D is an example of a confidence interval that does not include the population mean. The unknown population mean, because in real-world research you don't know the population mean. The unknown population mean is 9, and the range defined by this interval, well, the range goes from about 6.8 to 8.8. That range does not include 9. So this is one of the 5% of intervals that misses, so to speak, the population mean. And similarly, E looks like it spans from about 9.1 to 11.1. And similarly, it does not include the population mean. But I mean, the bigger picture here is that in forming a 95% confidence interval of the mean, I mean, you take the mean of your random sample, you carry out the necessary calculations, and formulas will be presented shortly. You go 2 standard deviations, which is to say 2 standard errors of the mean in both directions, and there is your resulting 95% confidence interval. And 95% of the time the confidence interval will do its job. That is, the range that it spans will include the unknown population mean. We've basically finished our confidence interval theory, and we're ready to do formulas. So, I mean, one almost technical point is to say that in a normal distribution, 95% of cases are located within 1.96 standard deviations of the mean, not within 2.00 standard deviations. And so for increased accuracy, our formula is going to use 1.96 in it. And so here are 2 equivalent formulas. I mean, it's really the same formula is repeated here and in different form for the 95% confidence interval. And these formulas require that n be 100 or greater. In this first formula, what you're doing is taking the study sample mean and you are adding and subtracting 1.96 times the sample standard deviation divided by the square root of n. And that formula can also be written as in below. Time to move on and then carry out some calculations. We will stick with the chapter 12 example. So in the chapter 12 you selected a random sample of 100 cases from a large statewide database of child abuse and neglect reports. So that big statewide database is your population. And you found that the mean age in your random sample was 8.5 years with a standard deviation of 4.9 years. So what is the 95% confidence interval of the population mean, mu, for children's ages? Let's carry out the calculations. The first step is to divide s by the square root of n to get our very good estimate of the standard error of the mean. And we know it's a good estimate because sample size is 100 or greater. If sample size was less than 100, we would not use this formula. Here is that calculation. The standard error of the mean, and I mean to say that the very good estimate of this is 0.49. So then let's multiply 0.49 times 1.96, and that's carried out in step 2. And that comes to 0.96. So that is 1.96 times the standard error of the mean's estimate. And then the final step and the computation of our confidence interval is adding and subtracting 0.96 from the mean of the random sample. So the 95% confidence interval computes to 7.54 to 9.46 years. So how do we interpret this confidence interval? So basically our interpretation is to say we can be 95% confident that the mean age of children in the large statewide database is between 7.54 years and 9.46 years. Now, this particular interval does indeed include the population mean of 9 years. We know the population mean is 9 years because we were presented with that in Chapter 12 for learning purposes. But in real-world research, you would not know the population mean. Indeed, your purpose is to establish a confidence interval for that mean. So in real-world research, we would not know assuredly that our calculated confidence interval included the population mean. But basically, based on the central limit theorem and the logic and theory that we work through for confidence intervals, we could be 95% confident we can be 95% confident that our confidence interval includes the population mean. And do see that that the confidence interval has an advantage over the point estimate. The point estimate simply says, well, our best estimate is such and such, but gives no sense of how good that estimate is, of how close the population parameter is likely to be to the estimate. Whereas, on the other hand, the confidence interval, which is also known as an interval estimate, does indeed provide this sense of closeness. We're 95% confident in our example that the population mean is between about 7.5 and 9.5 years. Let's examine the effect of sample size on the confidence interval. So let's go ahead and increase sample size to 400, and we'll presume that other factors stay the same. So what we need to do now is divide the standard deviation in our random sample by the square root of 400. So we're continuing to presume that the standard deviation in our random sample was 4.9, and we divide by the square root of 400. And so we estimate the standard error of the mean to be 0.245. So this is a smaller estimate. When sample size was 100, our estimate was 0.49. Let's continue with the calculation of the confidence interval. So we multiply times 1.96 to get 0.48, and then we're going to add and subtract from the mean of our random sample, which we presume still to be 8.5. So the resulting 95% confidence interval runs from 8.02 to 8.98. Now, again, in real-world research, we would not know whether or not this particular interval included the population mean. But on the other hand, we could be 95% confident that it did do so. The key point to see here is here's our confidence interval when sample size is 400. Here's our confidence interval when sample size is 100. So when we increase the sample size, we get a narrower confidence interval. We get a more precise estimate of the location of the population parameter. So when we increase the sample size, we're getting a better estimate, a tighter estimate. We're able to specify a narrower range for the population parameter. And so in this case, this is almost all incidental. It's the case that where sample size is 400, the confidence interval does not include the population mean, whereas it does do so when sample size is 100. But in real-world research, we would not know any of this. Our example is a little bit unrealistic, as in real-world research, you wouldn't know the population parameter. And this slide, focuses discussion on the points I was just making. The key point to see is that the confidence interval is narrower now, given the sample size of 400, than was the case when sample size was 100. So this is incorrect. It should say 7.54 to 9.46. So, other things being equal, increasing sample size always make the confidence interval narrower. In other words, it will give you a more precise, more accurate, indeed, a better estimate. Let's take a look now at the 95% confidence interval of the mean, the interval within which one is 95% confident that the population mean is located. Here are the formulas for that confidence interval, and we can, just as for the 95% confidence interval of the mean, we need sample size to be 100 or greater in order to be able to use these formulas. Just as a quick aside, where does this 2.58 come from? Take a minute and consult the normal distribution table at the back of the text. 99% of cases in a normal distribution are located within 2.58 standard deviations of the mean. So that's why we're using 2.58. So here are the calculation steps, and we're presuming all stays the same, and we're presuming sample size is back to 100. The 99% CI calculates to 7.24 to 9.76. Interpreting we can be 99% confident that mu, the unknown population mean, is located somewhere in the range that spans from 7.24 to 9.76. Note, this particular CI does indeed include mu, but in real-world research you would not know that this was so. Let's compare our 95 and 99% confidence intervals of the mean. And in both of these examples, sample size is 100. And observe that the 99% confidence interval is wider than is the 95% CI. Other things being equal, in particular sample size, the 99% confidence interval is always going to be wider than the 95% CI. You can look at the formulas to see that this is so. The 99% interval uses 2.58, whereas the 95 uses 1.96, so the multiplication that's in the formula simply produces the wider interval for the 99% interval. But the notion is, if you want to be 99% confident that the range that you're specifying includes the population mean, you've got to build a wider interval. And so you've sort of got a choice here. Do you feel 95% confidence is sufficient, in which case you can build the smaller and, in a sense, more precise interval, but you've only got 95% confidence that the population mean is in that range? Or you can, in a sense, be more conservative and build a wider interval, a less satisfying, less precise interval, but you're going to be 99% certain that it's doing its job. In other words, that the population mean is within that range. So neither of the intervals shown at the top of this slide is better than the other. One is narrower and therefore more precise, but you have less confidence that it includes the population mean. The other is wider, so therefore less precise, but you have greater confidence that it includes the mean. Other things being equal, it is the case that a 99% confidence interval is always going to be wider than is a 95% CI. Now, the 95% CI is much more common. So, this is tradition. Social science has, by tradition, decided that a 95% CI is kind of provides a good balance between precision and degree of confidence that the interval is doing its job. Let's go ahead and do one final calculation here. Let's calculate a 99% CI where sample size is 400. So it's a 99% CI, so we're using 2.58 in the formula. Sample size is 400, so we're dividing by the square root of 400. So this confidence interval is clearly going to be narrower than the 99% CI when a sample size was 100. And we carry out the calculation. 7.87 to 9.13 is the confidence interval, and we can be 99% confident that the mean age of children in the full population is within the range that spans from 7.87 to 9.13. And do observe that this interval is narrower than the 99% CI when n was 100. There the interval spanned from 7.24 to 9.76. So this comparison here, is pointing out to you that whether you're working with a 95% confidence interval or a 99% confidence interval, when the sample size goes up, both of those confidence intervals are going to shrink. So to this point, we've gone through the theory of confidence intervals and also demonstrated confidence intervals for means. So the remainder of the chapter is going to focus on forming confidence intervals for proportions, and also provides some miscellaneous information